So today let's just discuss the remaining questions of limit, continuity and differentiability. So the question 1 for today is, we are supposed to check the continuity of this function fx at point 0, 0. Wait a minute. So the function fx, y is given to me as sine inverse x plus 2y upon tan inverse 2x plus 4y when my x comma y are both are not 0 simultaneously, and 1 by 2 when x comma y is equals to 0, 0. So to check continuity, it's enough to check if limit when x comma y approaches 0 is equals to f0, 0. So we're supposed to check this limit on left hand side. So let us assume that y is equals to mx. So my limit x comma y approaches 0, 0, fx comma y will be equals to limit x approaches 0 fx comma mx. I am able to do so because if this limit exists, then it will be same, because limit is unique no matter what path which follow. So I am calculating my limit at this path and we'll see if it turns out to be independent of this m or not. If it turns out to be independent, then my limit is unique, otherwise the function is discontinuous. So let's just find out this limit. So it will be limit x approaches 0 sine inverse x plus 2 y, that is mx, divided by tan inverse 2x plus 4 y, that is 4mx. This term is equals to limit x approaches 0 sine inverse x plus 2mx divided by tan inverse 2x plus 4mx, and this thing is equals to limit x approaches 0 sine inverse x plus 2mx divided by 2x plus 4mx upon tan inverse 2x plus 4mx divided by 2x plus 4mx. I am able to divide this term with 2x plus 4mx because x comma y are not equals to 0, that is x and y are not taking value 0 simultaneously. So that's why I am able to divide this term with x plus 2x plus 4mx plus 2x plus 4mx. So this term is basically equals to limit x approaches 0 sine inverse x plus 2mx divided by x plus 2mx into 2 divided by tan inverse 2x plus 4mx upon 2x plus 4mx. And we know that limit x approaches 0 sine inverse x upon x is equals to 1, and limit x approaches 0 tan inverse x upon x is also equals to 1. So if we calculate this limit, so this limit will basically 1 by 2 into 1 upon 1, which is 1 by 2, and this is equals to f of 0, 0. So my function fx x comma y is continuous at 0, 0. And these are basically the standard results of limit. You can just remember these comes handy in examination as it helps to save time. So let's move on to next question. So the next question says that fx is a real valued function. So fx is real valued function and it's defined on interval -5, 5, such that e raised minus x into fx is equals to 2 plus 0, x under root 1 plus t raised 4 dt for all x belonging to -5, 5. And it is given that f inverse x is inverse function of fx. So f inverse x is inverse of fx. So we are supposed to find f inverse, derivative of f inverse x at x equals to 2. So we are supposed to find this. So if f inverse is inverse of f, so f inverse f of x will be basically equals to x. That is, composition of f inverse and f will be equals to identity function. So if I differentiate with respect to x, so I'll be getting f in derivative of f inverse fx into f dash x is equals to 1. So I have used chain rule here. So first I have taken derivative of this term and then a derivative of this thing. So from here I'll be getting f inverse, derivative of f inverse fx is equals to 1 upon f inverse x, and I am supposed to find f inverse derivative of f inverse at 2, that is equals to 1 upon f dash x, and here 2 is basically equals to fx. So if I can find out value of x for which f is taking value 2, so I can basically find this thing easily. So my given function fx is basically e raised minus x fx equals to 2 plus 0 to x under root 1 plus t raised 4 dt. So if I take x equals to 0 here, so I'll be getting f of 0 is equals to 2. This term will become 0 because integration will be from 0 to 0. So that is 0 only. So at x equals to 2, at x equals to 0, f is taking value 2. So my f derivative of f inverse at fx equals to 2 is basically f dash 0. Now I am supposed to find out value of this f dash at x equals to 0 to find this. So let's take derivative of this when with respect to x. So if I differentiate it with respect to x, I'll be getting minus of e raised minus x fx plus e raised minus x f dash x is equals to, this term will be 0 and derivative will be 0 to x into dy dx under root 1 plus t raised 4 dt plus under root 1 plus x raised 4 into 1 minus 0. And since there is no term involving x, so this will be 0. So I got e raised minus x into f dash x minus fx is equals to 1 plus x raised 4. And I'm supposed to find value of f dash 0. So if I take x equals to 0, I'll be getting f dash 0 minus f0 is equals to 1. So from here my f dash 0 is 1 plus f0 and I have calculated f0 as 2. So my f dash 0 is basically 3. So derivative of f inverse at 2 is basically 1 upon f dash 0, that is 1 upon 3. So this is the value of derivative of f inverse at 2. Now let's move on to next question. So the next question is under root x plus y plus under root y minus x is equals to c, and we are supposed to find d square y by dx square. So first let us just simplify it for y. So we'll be getting under root x plus y is equals to c minus under root y minus x. I can take whole square on both sides, so I'll be getting x plus y is equals to c square plus y minus x minus 2c under root y minus x. Now if I simplify it, this y balances out this one, so I'm left with 2x minus c square is equals to minus 2c under root y minus x. I can take a whole square of both sides, so I'll be getting 2x minus c square whole square is equals to minus 2c under root y minus x whole square, which is basically equals to 4x square plus c raised 4 minus 4x c square, which is equals to 4c square into y minus x. So if I simplify it, I'll be getting 4x square plus c raised 4 minus 4x c square is equals to 4y c square minus 4x c square. This term balances out this one. So from here I got my y as 4x square plus c raised 4 divided by 4c square, and this thing is equals to y is equals to x square by c square plus c square by 4. Now I got y in terms of x, so I can easily find out dy by dx by taking derivative with respect to x. So it will be 2x by c square plus 0, and if I again take derivative with respect to x, so I'll be getting d square y by dx square equals to 2 by c square, and this is what we are supposed to prove in this question. So let's move on to next question. So the next question says that show that the function this is continuous but not differentiable at x equals to 0. So fx is given to me as x e raised 1 by x minus 1 upon e raised 1 by x plus 1. X is not equals to 0 and 0 when x is equals to 0. So if I take left hand limit, so to prove continuity, I am supposed to show that limit x approaches 0 negative of fx is equals to limit x approaches 0 positive fx is equals to f of 0, and that is 0. So let's find out left hand limit, that is limit x approaches x, when this is basically equals to limit h approaches 0 f 0 minus h. So if I find this limit, it will be limit h approaches 0 minus h into e raised minus 1 upon h minus 1 upon e raised minus 1 upon h plus 1. So since my h is approaching 0, so my 1 by h will approach infinity, and e raised 1 upon h will also approach infinity. So using that result, it will be 0 into this. This is basically 1 upon e raised 1 by h. So this term will approach 0. This term will approach 0. So it is 0 minus 1 upon 0 plus 1. This is equals to 0. Likewise, my right hand limit will be limit x approaches 0 positive fx, and that would be basically limit h approaching 0 f of 0 plus h, which is limit h approaches 0 h into e raised 1 by h minus 1 into e raised 1 by h plus 1, and this is equals to limit h approaches 0 h into 1 minus e raised minus 1 by h upon 1 plus e raised minus 1 by h. This term will approach 0 and this will also go to 0. So my this limit is 0 into 1 minus 0 upon 1 plus 0, that is 0. So my left hand limit is equals to my right hand limit, which is equals to 0. So my function fx is continuous function. Now let's check differentiability. So we are supposed to show that it is not differentiable at x equals to 0. So what we can do is we can just find out derivative at x equals to 0 approaching from negative side and positive side, and then we can see if they match or not. So my left hand derivative will be limit x approaches 0 negative fx minus f0 upon x minus 0, that is limit h approaches 0 f0 minus h minus f of 0 upon minus h. This is equals to my f of 0 is 0, so this is limit h approaches 0 f of minus h upon minus h. So this thing is equals to limit h approaches 0 minus h into e raised minus 1 upon h minus 1 upon e raised minus 1 upon h plus 1 divided by minus h as well. This minus h balances out this one. So my limit will be minus of 1, because this will approach to 0 and this will also approach to 0. So it will be 0 minus 1 upon 0 plus 1. That gives me minus 1. Likewise, my right hand derivative will be limit x approaches 0 positive fx minus f0 upon x minus 0, and that would be limit x approaches 0, h approaches 0, 0 plus h minus f0, that is 0 only, divided by h. So this will be equals to limit h approaches 0, h into e raised 1 by h minus 1, e raised 1 by h plus 1, and this thing will be equals to divided by h. This balances out this one. So this will be equals to limit h approaches 0, 1 minus e raised minus 1 by h upon 1 plus e raised minus 1 by h. This term approaches 0 and this also approaches 0. So my limit will be 1 minus 0 upon 1 plus 0. So my right hand derivative is basically 1. And you can clearly see that left hand derivative is not equals to right hand derivative. So fx is not differentiable at x equals to 0. So let's move on to next question. So the next question says that show that the function fx this has a removable discontinuity at origin. So discontinuity at any point x equals to a is said to be removable if both left hand limit and right hand limit exists and are equal, but they are not equals to value of f at that point a. So if we are able to show this, then we can say that this function fx has removable discontinuity. So let's find out. Limit x approaches 0 negative fx will be basically limit h approaches 0 f of minus h. That will be limit h approaches 0 sine of minus 2h upon minus h. So this will be equals to limit h approaches 0. I can multiply and divide by 2. So it will be minus sine 2h upon 2h, because sine of minus x is equals to minus of sine x. So and this limit, and we know that limit x approaches 0 sine x upon x is equals to 1. So this limit turns out to be 2. Likewise, my right hand limit will be, this is left hand limit, and my right hand limit will be limit x approaches 0 fx is equals to limit h approaches 0 f of h, which is basically equals to sine 2h upon h. I can multiply and divide by h, so by 2. So I'll be getting 2 into sine of 2h upon 2h, which is equals to 2. So my left hand limit is equals to right hand limit, that is 2. But my function fx is taking value 1 at x equals to 0, which is not equals to f of 0. Thus my function fx has removable discontinuity. I can define value of function fx at x equals to 0 as 2. So then this discontinuity can be easily removed and the function fx can be made continuous. So let's move on to next question. So the next question says that show that the function fx defined as this is discontinuous at every point in R. So my fx is basically 1 when x is belonging to irrational and minus 1 when x is belonging to rational. So this is again a Dirichlet function, and we can do it like we did in previous video. We can assume that a is any rational function, any rational point. A is any rational number. So if a is rational, then f of a will be basically minus 1. But since set of real numbers is dense, then for every positive n, we can find an irrational an such that an converges to a, that is an minus a is less than 1 minus n. And since we assume that let fx be continuous function, So if my fx is continuous, then by sequential criteria f of an must be equals to f of a. That is limit f of an and approaching infinity must be equals to f of a. But my f of an, where an is any irrational number, will be basically 1. But that is not equals to my f of a, that is -1. So we got a contradiction because my 1 is not equals to -1. So my assumption that fx is continuous for any rational a is incorrect. Likewise, I can assume any irrational b, then my f of b will be basically 1. And then using the dense condition of a set of real numbers, I'll be getting bn approaching b, and then my f of bn must be equals to f of b using sequential criteria. But my f of bn will be basically -1, which is not equals to f of b, that is 1. So again we got a contradiction. So this is a fairly repeated question. You can just move like this, like twice or thrice this question has been asked previously. So let's move on to next question. So the next question says that evaluate this limit where fx is this. So my fx is x square minus 4 upon x minus 2 when x is not equals to 2, and pi when x is equals to 2. So I am supposed to find limit x approaching to x square minus 4 x minus 2. So either I can substitute limit directly x equals to 2, but then it will be 0 upon 0 form. So I can use L'Hopital, or I can do is I can write it as x minus 2 into x plus 2 divided by x minus 2. And since my x is not equals to 2, so this term balances out this one. So my limit is equals to limit of x plus 2, which is equals to 4. So limit x approaches to fx is equals to 4. And this is not equals to pi, so this is a removable discontinuity again, but that's not asked in the question. We are supposed to just find the value of limit. So let's move on to next question. So the next question says that ft is any function such that it is taking value 0 when t is less than 0, t when t is taking value in between closed interval 0, 1, and 4 when t is greater than 1. And we are supposed to calculate a function capital F of x that is defined as integration from 0 to x of fx. So in this as well we can construct cases. So when my x is equals to 0, then my capital fx will also be 0. When my x is less than equals to 1, then my capital fx will be 0 to 1 t dt, that is t square by 2, 0 to 1, that gives me 1 by 2. Likewise, when my x is greater than 1, then my capital fx is equals to 0 to x small ft dt, which is equals to 0 to 1 ft dt plus 1 to x ft dt. I write it because my function small fx is defined as a piecewise function, so I can just write it like this. So my 0 to f is taking value t from 0 to 1 and value 4 for t greater than 1. So this will basically give me t square by 2 limit 0 to 1 plus 4t 1 to x. So this gives me 1 by 2 plus 4 into x minus 1, that is basically 4x minus 4 plus 1 by 2, which is equals to 4x minus 7 by 2. So my capital fx function is 0 when t is less than 0, 1 by 2 when t belongs to closed interval 0, 1, and 4x minus 7 by 2 when t is greater than 1. And we are further asked that where is capital F function non-differentiable. So we are supposed to check its differentiability. So if you see that you can clearly observe that the function capital Fx is non-differentiable at x equals to 0 because it's not continuous there. So x equals to 0 is one point of discontinuity. Now we are supposed to check its continuity or differentiability. Yeah, differentiability. So first we are supposed, again another point of discontinuity can be at t equals to, that is x equals to 1. So first let's check continuity at x equals to 1. So left hand limit is basically 1 by 2 and right hand limit is basically 4 into 1 by 2 minus 7 by 2, that is 4 by 2, that is 2 minus 7 by 2, that is minus 3 by 2. Yeah. But my left hand limit is not equals to my right hand limit. So capital Fx is discontinuous, hence non-differentiable at x equals to 1 as well. So point of non-differentiability are x equals to 0 and x equals to 1. So let's move on to next question. In this question it is given that f is a function defined on R and f is defined as this. So what is given to us is f is a function defined on R to R. So it is given that f of x plus y is equals to f of x plus f of y for all x and y in real set. So it says that if f is differentiable at one point of R, then we are supposed to prove that f is differentiable on whole R. So first let us assume that let a belongs to R be a fixed point, and let's assume that f is differentiable at this point A. At point A. So using definition of differentiability, I'll be getting f dash A as limit h approaches 0 f a plus h minus f a upon h. So this will be equals to limit h approaches 0. On f a plus h I can use this definition, so I'll be getting f a plus f h minus f a upon h. This f a balances out this one, so my f dash a is basically equals to limit h approaches 0 fh upon h, and this limit exists because we have assumed that f is differentiable at point A. So this limit exists. Now we are supposed to prove that f is differentiable on whole R. So let us assume that let C belongs to R be any arbitrary point, point in R. So now I can show that f is differentiable on C, and since I have assumed that C is any arbitrary point in R, so I can conclude from there that C will be differentiable on whole. So this limit exists because f is differentiable at point A. Now let C be any arbitrary point in R. Now if I can show that the function f is differentiable on C, and since C is any arbitrary point in R, so my function f will be differentiable on whole set R. So let's see if we can check differentiability of function f at C. So limit h approaches 0 fc plus h minus fc upon h. If this limit exists, then I can say that my function will be differentiable at c. So this will be basically limit h approaches 0. On fc plus h, I can write as fc plus fh minus fc divided by h. This fc balances this one. So my f dash c will be basically equals to a limit h approaches 0 fh upon h. But this limit exists from definition of this f dash a. Let's name it as 1. So from here, from 1, I can say that f dash c exists. So my function f is differentiable at c in R. But c, I have assumed that c is any arbitrary point. C is any arbitrary point. So from here I can say that f is differentiable on whole R. And that's what we're supposed to prove in this question. So let's move on to next question. So the next question says that the function fx equals to this. So my function fx is defined as x square sine 1 by x if x is not equals to 0 and 0 if x is equals to 0. So we are supposed to find f dash x, and we are supposed to check if f dash x is continuous at x equals to 0. So let us see that what f dash x would be. So f dash x would be basically 2x into sine 1 by x plus x squared into cos 1 by x into derivative of 1 by x, that would be minus 1 upon x square. So this is basically equals to 2x sine 1 by x minus cos 1 by x. This will be my f dash x when x is not equals to 0. And when x is equals to 0, f dash x is equals to 0 when my x is equals to 0. So my f dash x is basically equals to 2x sine 1 by x minus cos 1 by x when x is not equals to 0, and 0 when my x is equals to 0. So this is my f dash x. Now I am supposed to check if this f dash x is continuous at x equals to 0 or not. So if f dash x is continuous at x equals to 0, then my limit x approaching 0 f dash x must be equals to f dash 0. F dash 0 is 0, so this limit must be equals to 0 for f dash x to be continuous. So let us check if limit x approaches 0 f dash x is 0 or not. So it is 2x sine 1 by x minus cos 1 by x. This will be basically equals to limit x approaches 0, 2x sine 1 by x minus limit x approaches 0 cos 1 by x. So this will be basically 0 minus limit x approaches 0 cos 1 by x. But this limit does not exist. So the limit x approaches 0 f dash x doesn't exist. So we cannot say if it will be 0 or not. So from here I can say that my f dash x is not continuous at x equals to 0. So let's move on to a next question. So the next question says that f is a function from R to R. F is a function from R to R, and f is defined as f of x plus y equals to fx into fy for all x comma y in R. And also fx is not equals to 0 for any x in R. So we are supposed to show that. So we claim that my f dash x is equals to fx for all x belonging to R. So we are supposed to prove this relation, and it is given that f dash 0 is equals to f0 and the function f is differentiable for all x in R. So it is given that my function f is differentiable for all x belongs to R. So in the question they have given us a function f from R to R and which is differentiable for all x belonging to R, and also the function f satisfies certain property, that is f of x plus y is equals to fx into fy, and function is taking non-zero values for all values of x, and f dash of 0 is equals to f of 0, and we are supposed to prove that f dash x is equals to fx for all x. So to prove that, definition of f dash x will be basically limit h approaches 0 fx plus h minus fx upon h, but my fx plus y is fx dot fy, so this limit will be reduced to limit h approaches 0 fx dot fh minus fx upon h. So I can take fx outside, so my limit will be limit h approaches 0 fx into fh minus 1 upon h. This basically gives me fx into limit h approaches 0 fh minus 1 upon h. Now I am supposed to find out value of f0. So from fx plus y is equals to fx fy, if I take my x equals to y is equals to 0, so my f of 0 will be basically equals to f of 0 whole square. So from here I'll be getting f of 0 equals to 0 or f of 0 is equals to 1, but in question it is given that f of x is not equals to 0 for all x in R, that is f is taking non-zero value for all x in R, so my f of 0 cannot be equals to 0, so I can discard this case. So from here I'll be getting f of 0 as 1. So if f of 0 is 1, then my limit h approaches 0 fh minus 1 upon h will be basically 0 upon 0 form. So to solve it further, I need to use basically the L'Hopital rule here. So if I use L'Hopital rule here, so I'll be getting fx into limit h approaches 0 f dash h upon 1. So this will be basically equals to fx into f dash 0, but in question it is given that f dash 0 is equals to f0, and I have found out that f of 0 is equals to 1. So from here I got my f dash 0 as 1. So my f dash x is basically equals to fx into 1 for all x in R. So I have proved that my derivative of f dash x is equals to fx only. So this is what I am supposed to prove in this question. So let's move to next question. So the next question says that show that f is a function from closed interval ab to R is a continuous function, that then range of f is also a closed interval CD for some real values c and d. So it is given that f is a function from closed interval a comma b to R. Also f is a continuous function. Then we claim that f of a comma b is equals to c comma d for some c comma d in real numbers and c is less than equals to d. So if you see that this set a comma b is basically subset of R and it is basically a closed set and a bounded set. So from here I can say that my a comma b is a compact set, because in real a closed and bounded set is a compact set. Likewise I can say that my C comma D is also a compact set. So my question reduces to the following, that a continuous function maps a compact set to a compact set. That is, our claim is a continuous function maps a compact set to a compact set. And we know that a set is compact if for any open cover, if for any open cover there exists a finite subcover. So let us assume that let V alpha, where alpha belongs to the index set, be any open cover of fx. So if that's the case, then fx will belongs to union of V alpha, where alpha belongs to index set, for all x belongings to a comma b. So from here I can say that it's the f of capital X, where I am assuming x be taking any elements from this set a comma b. So my capital X will be basically contained in f inverse of union alpha belongs to index set V alpha, and I can write it as x will be contained in union of alpha belonging to inverse set f inverse V alpha. Now we have assumed that V alpha is basically an open set, and this set V alpha, where alpha is an index set, acts as open cover of fx. So from here I can say that f inverse V alpha is open in a comma b, because f is my continuous function and V alpha is also open. So a continuous function maps open set to open set. So using that I can say that f inverse V alpha will be open in a comma b. And we know that arbitrary union of open set is open. So from here I can say that union of f inverse V alpha will be open, and since x is contained in union of alpha belongs to index set f inverse V alpha, so from here I can say that f inverse V alpha is open cover of x, that is a comma b. But we know that x, that is a comma b, is compact set. Then by definition of compact set, there exists a finite subcover. So let us assume that let f inverse V alpha I, where I is in between 1 to n, be finite subcover of x. So from this, x must be contained in union of I from 1 to n f inverse V alpha. So from here I can say that my f of capital X will be contained in f of union I equals to 1 to n f inverse V alpha, and this is basically equals to union of I equals to 1 to n f of f inverse V alpha I. Here it is V alpha I, f inverse V alpha I, which is basically equals to union of I equals to 1 to n f alpha I. Thus we got an open finite subcover of this fx as well. So fx has a finite subcover. So from here I can say that my fx is a compact set. So fx is closed and bounded, because in real a compact set is closed and bounded, so fx will be of some form like c comma d. So this is what we are supposed to prove in this question. So let's move on to next question. So the next question says that fx is equals to mod of x by 2 plus 1 if x is less than 1, and x by 2 plus 1 if 1 less than equals to x less than 2, and 1 minus mod of x by 2 if 2 is less than equals to x. So they have asked us what are the points of discontinuities of f if there is any, and further they have asked us what are the points where f is not differentiable. Okay, so we are supposed to find the point of discontinuity and the points where f is not differentiable. So first let us write f in a simplified form. So f will be basically minus x by 2 plus 1 if my x is less than 0, and x by 2 plus 1 if my x is greater than equals to 0 but less than 1. Likewise x by 2 plus 1 if my x is greater than equals to 1 but less than 2, and 1 minus x by 2 if my x is greater than equals to 2. So I can write it as minus x by 2 plus 1 if x is less than 0, x by 2 plus 1 if 0 less than equals to x less than 2, and 1 minus x by 2 if my x is greater than equals to 2. So this is my fx, and I am supposed to find the point of discontinuity and point of non-differentiability. So the only possible points of discontinuity and non-differentiability can be either 0 or 2. So we are supposed to check continuity and differentiability at points 0 and 2. So first let's check continuity, because that's the necessary condition for differentiability. So continuity of fx at x equals to 0 will be basically, I'm supposed to check limit x approaches 0 negative fx. If this holds or not, I'm supposed to check that is equals to f of 0. So if you find f of 0 will be f of 0 is basically 1, and f of x approaches 0 negative fx will be basically equals to limit x approaches 0 1 minus x by 2, that is also 1, and limit x approaches 0 positive fx is limit x approaches 0 1 plus x by 2, that is 1. So from here I can say that my function f is continuous at x equals to 0. Now let us check that if it is continuous at x equals to 2 as well. Continuity at x equals to 2. So we are supposed to satisfy this condition, check if this condition holds or not for x equals to 2. So that is, so first let us check what will be f of 2. So my f of 2 is basically 1 minus 2 by 2, that is 0. Now let's find out what these left hand limit and right hand limit will be. So my left hand limit will be 1 plus x by 2, that gives me 2, but my right hand limit is limit x approaches to 1 minus x by 2, that gives me 0. So my left hand limit is not equals to right hand limit. So f is not continuous at x equals to 2, but continuity is necessary condition for differentiability. So from here I can say that f is not differentiable at x equals to 2. Now let us check differentiability of function f at x equals to 0. So for that, differentiability at x equals to 0. So my left hand derivative would be a left hand derivative, that is limit x approaches 0 negative f 0 plus h, limit h approaches 0, 0 minus h minus f of 0 upon h. So this is basically equals to limit h approaches 0, f of minus h would be, so this would be basically equals to 1 minus h by 2 minus f of 0, that is 1 divided by h, so it gives me minus 1 by 2, and my right hand derivative would be basically limit h approaches 0, f 0 plus h minus f of 0 by h is equals to limit h approaches 0, 1 plus h by 2 minus 1 by h. This gives me a right hand derivative as 1 by 2, but you can see that left hand derivative is not equals to right hand derivative, so function f is not differentiable at x equals to, not differentiable at x equals to 0. So the point of discontinuity is only x equals to 2, but point of non-differentiability is both x equals to 0 and x equals to 2. That's what we are supposed to find in this question. So let's move on to next question. So the next question says that obtain the values of the constant a, b and c for which the function is defined as this. So function is basically sine a plus 1x plus sine x upon x when x is less than 0, c when x is equals to 0, and x plus b x square raised 1 by 2 minus x raised 1 by 2 upon b x raised 3 by 2 when x is greater than 0. So it is given that function is continuous at x equals to 0, and we are supposed to find constant values of a, b and c. So let's do that. So since function is continuous at x equals to 0, so limit x approaches 0 negative fx must be equals to limit x approaches from right hand side of fx, and that must be equals to f of 0. So my f of 0 is basically c. This I got from continuity at x equals to 0. So my f of 0 is c, and my left hand limit will be basically limit x approaching 0 sine a plus 1x plus sine x by x. So this will be basically equals to limit x approaches 0 a plus 1 into sine a plus 1x by a plus 1 into x plus sine x upon x. So I can write this limit as a plus 1 into 1 plus 1. I can write this because I know that limit x approaches 0 sine x upon x is equals to 1. So using this, taking this limit inside brackets, so I'll be getting this. So this is equals to a plus 2. Likewise, my right hand limit will be basically limit x approaches 0 x plus b x square raised 1 by 2 minus x raised 1 by 2 divided by b x raised 3 by 2. So this is basically equals to limit x approaches 0 x raised 1 by 2 1 plus b x raised 1 by 2 minus 1. I have taken x raised 1 by 2 out from this, so I am left with b x raised 3 by 2. So this is basically equals to limit x approaches 0 1 plus b x raised 1 by 2 minus 1 upon bx. I have balanced this x raised 1 by 2 from here, so I am left with this. So if I put value of limit here, I'll be getting 0 upon 0 form. So I have to use L'Hopital rule here. So using L'Hopital rule, I'll be getting 1 by 2 1 plus bx raised minus 1 by 2 into b upon b. This b balances out this one, so I got my limit as limit x approaches 0, 1 upon 2, 1 plus b x raised 1 by 2. So if I put x equals to 0, I'll get this limit as 1 by 2. So using the continuity condition, I'll be getting 1 by 2 is equals to a plus 2 is equals to c. So from here I got my c as 1 by 2, a as 1 by 2 minus 2. So my a is basically minus 3 by 2. And since I got no condition involving b, so b doesn't play any role in, b doesn't affect the limit, the continuity of function fx in any way. So I can choose any arbitrary value of b. So b belongs to R, that is any arbitrary real b would work. So that's what I'm supposed to find in this question. We are supposed to find only values of a, b and c for which this function fx is continuous at x equals to 0. So these are the only questions asked related to limit, continuity and differentiability topic. So thank you for watching.